The following presentation is brought to you by Discovery Channel School, a leading provider of quality educational resources that help teachers bring the world to their students.
This is TLC Elementary School, a place where teachers of kindergarten through 6th grade can find high-quality documentary programs chosen to inform and delight students. Use TLC Elementary School to complement your classroom lessons and to give students an up-close look at the world and the people around them. On this edition of TLC Elementary School, see how grams and grains, meters and miles measure up in measurement and scale. First, get the skinny on weight and see how the first scales sized up. Then discover the long and short of things in length. Finally, learn a bit about scale as you take a trip through the solar system. And watch for classroom activities right after each segment. Segment 1. Weight.
The minute we come into the world, people are sizing us up. Let's face it, we're obsessed with weight. Whether we're baking a cake, cooking up some chemistry, or loading a truck, weight matters. It's important to know exactly how light or heavy things are. But why? It all started with trade. Early people wanted to know whether they were getting as much as they paid for. So they started weighing goods. It was hardly an exact science, mostly just lifting and comparing. But as trading became more widespread, knowing the exact weight of an object became even more important. Since weight determined an object's value, traders needed a more accurate means of measuring. Around 3500 BC, the ancient Egyptians invented the scale. Goods were hung from one pan. Weights were added to the other until a perfect balance was achieved. Simple, yet precise. The first scales had to be precise because they were invented to weigh something very valuable: gold. Since gold was traded in such small quantities, tiny weights of an equal size were needed to measure it out. So ancient people decided to use grains and seeds as standards of weight. A grain of wheat became the grain of weight. Mustard seeds weighed gold in India. The seeds of the carob tree gave us the carat, still used to describe the weight of diamonds today. And because gold and silver could now be weighed, they could also be used as money. The first coins were just lumps of precious metal, so a gold coin was simply worth its weight in gold. But our weight problems didn't go away. Dishonest traders and merchants often shaved small amounts of metal off coins, making them less valuable. Nevertheless, history proves that not all trade was risky business. During the Middle Ages, big trade fairs were held in Troyes, France. The weights and measures used there were carefully monitored to ensure that people didn't feel cheated and would keep coming back. Supposedly, it was here that the Troy pound came about, a 12-ounce pound used to measure precious metals. In the 1500s, Britain's Queen Elizabeth I built the first system of weights on the Troy pound. Monarchs kept a tight rein on weights and measures. Bakers caught selling underweight loaves ended up in the stocks. To cover themselves, they baked an extra loaf to add to every 12 they sold, now known as the baker's dozen. So here's a question millions of people want the answer to. How do you lose weight without dieting? First, weigh yourself. Next, find a high mountain and climb it. Then weigh yourself on the summit. Bingo! You've lost weight, maybe as much as half a pound. Weight is determined by gravity. The farther away from the center of the Earth you go, the less the pull of gravity, so the lighter you'll be. Although you might weigh less on top of a mountain than you would at sea level, your mass would be exactly the same. Mass, or the amount of matter you contain, remains the same wherever you are. We often use the word weight when what we really mean is mass. It's a difference that is critical to scientists. In their world, accuracy is everything. For years, science and business were hurt because there was no universal system for measuring weight. Different countries used different units. The French Revolution in 1789 changed all that. The explosion of new thinking allowed scientists to design a new system of measurement from scratch. They wanted to tie together all the different physical properties of a substance using interrelated units. The new standard of length, the meter, was to be the starting point of the new unit of mass, the kilogram. The meter and kilogram are two of the basic units in the metric system, which is used around the world today. Imagine a cube whose sides are 1/10 of a meter long. Fill it with water right up to the brim. The weight, or more correctly, the mass of this water, is said to be exactly 1 kilogram. The clever thing about this concept is that the volume of this same amount of water gives us the liter. The first kilogram was a slug of platinum and iridium, made to match precisely the weight of that liter of water. All the world's weights are calibrated to this single lump of platinum and iridium, affectionately known as Le Grand K. Other copies, or officially national prototypes, were sent out from Paris to other countries, and this international Kilo Club has provided the world with a reliable and universal standard. But everything is not quite as perfect as it seems. There's whispering behind the scenes that Le Grand K may have a weight problem. There's a rumor that it may be losing weight, or more correctly, mass. Or it may be that the copies are putting mass on. It was discovered that as a group, the copies were slightly heavier than the master. One theory is that the process of cleaning changes the mass. The difference in mass between the Grand K and its copies is very small, but it is enough to remind us that man-made objects can be unreliable. The search continues for the ultimate standard of mass, but the world waits, and until then, Le Grand K, with its small imperfections, will have to do.
Try this activity to complement weight. Measure a grape using a scale, ruler, and measuring cup with water. Record its weight, length, and volume. Compare your measurements with others in the class. Then measure 2 grapes together. How do the measurements compare? Segment 2. Length.
You may not realize it, but measurement rules your life. It tells you what kind of clothes you need to buy, and how far you can go on a tank of gas. That's a good thing, really. Measuring things has helped us give a kind of order and logic to our vast universe and to our everyday lives. Take length. The long and the short of it is, we frequently need to know how far it is from one point to another. To buy a pair of shoes that fit, you need to know how long your foot is. To get you to school on time, your parents need to know how far away your school is. We take all this for granted now, But how did we first come up with rulers, miles, feet, and all the rest? In the beginning, man was his own measure. 2 steps made 1 pace. 1,000 paces made a mile. Fingertip to fingertip made a fathom. That's 6 feet. And the distance around the waist of a man was a girth, or 3 feet. But what was a foot? Well, the foot was a foot, like the hand was a hand. The finger was a finger, and a span was the distance from pinky to thumb. But the ruler of rulers was the elbow, or as it was better known by its Latin name, the cubit, the distance between elbow and fingertip. The ancient Egyptians used cubit rulers to achieve amazing precision in their architecture. The sides of the Great Pyramid of Giza are more than 750 feet long, and they're only off by this much. You don't hear much about cubits anymore, but the fabulous foot still has legs. It has ambled around different civilizations for thousands of years. And of course, it's still used in the U.S. customary system. In ancient Rome, the foot was both a unit of length and weight. It was the length of a special copper bar which had been fashioned to weigh exactly 1 pound. The bar was divided into 12 equal parts called unciae. As a unit of both weight and length, it was the source of the modern terms ounce and inch. Unfortunately, from country to country, the average length of the male foot varies. This sort of measurement mayhem eventually caused big problems for the very first traders. As units of length varied from place to place, no one knew how much of anything they were buying. A yard of fabric in France might be different from a yard of fabric in India. Traders decided they needed an absolute standard. Henry I, a king of England in the 12th century A.D., decreed that the standard yard was to be the distance from his nose to his fingertips, a little less than 3 feet. He commanded that an iron bar be forged to this length. In the 16th century, Britain's Queen Elizabeth wanted to put her own stamp on Henry's yard. Adding her initial E made the official yardstick almost exactly 36 inches long. But in 1834, a mighty fire ravaged England's Houses of Parliament. One of the most precious pieces of metal in the land, the standard yard, was lost. Scientists saw their chance. They could do away with a system based on the length of some monarch's limb, which of course varies from monarch to monarch. They wanted their new yard to be based on the laws of science, so that it could always be accurately reproduced. So, where did they look? To a pendulum. Back in 1581, the 17-year-old Italian scientist Galileo was fascinated by a candelabra he saw swinging in Pisa Cathedral. He timed the candelabra's swings with his pulse and observed that the time it took to travel from one end of its swing to the other was always the same. He went on to prove that it made no difference whether the swing was big or small. What determined how long the swing lasted was the length of the pendulum. Galileo's 200-year-old observations provided the principle scientists wanted to take advantage of. Their yard was to be the length of a pendulum that would generate a swing of exactly 1 second in duration. On paper, the theory was sound, but in practice, they couldn't make it work. The fluctuating effects of gravity upset their designs. The British had failed in their attempts to create an absolute standard of length. The French were more successful, thanks to the French Revolution of 1789. It was a revolt against bad rulers, to be sure, but not the kind you measure with. Still, a new way of thinking about measurement emerged. It was called the metric system. The metric system took as its starting point a new unit of length. Scientists proposed that this new unit, the meter, be derived not from the human body, but from an established scientific constant, the circumference of the Earth. 1/10,000,000th of the distance between the North Pole and the equator was to be 1 meter. A survey of this distance ended up taking 10 grueling years. Mathematicians used the survey results to calculate the distance from the pole to the equator. A bar, precisely 1/10,000,000th of this distance, was then constructed from platinum. Stand aside, cubit, yard, and chain. Be off, inch and foot. Make way for the meter. Unfortunately, explorers later discovered that the Earth was not a regular shape. Once again, we were a long way off from a standard unit of length. Now, at last, scientists have finally gotten it right. And it took until the end of the 20th century to get there. Length is now based on, are you ready for this? Speed. The speed of light, that is. It's a bit quick, but at least it's constant. The meter is now the distance traveled by a beam of light in a tiny fraction of a second. To be precise, about 3/10000000ths of a second. That's not a very long time, but trust us, it's a distance you can count on.
Try this activity to complement length. Using your foot as a ruler, calculate the length of a wall in your classroom. Compare this length with others. Then, measure the wall using the standard 1-foot unit. How did your measurements size up with the standard length? Segment 3. Scale.
This is astronomer Sheldon Schaefer, and he's actually pedaling from one planet to another. In fact, he's converted the entire city of Peoria and its immediate surroundings into a scale model of the solar system.
There really is no other way to show how big space is and how small we are than to build a scale model like this.
Why? To help us glimpse the vastness of space.
If you really want to look at the whole scale of the universe, our solar system is just our doorstep. We're on a planet going around a star. The star is one of 100 to 200 billion stars in our Milky Way galaxy. Our Milky Way galaxy is one of 24 galaxies of the local group of galaxies. The local group of galaxies is part of the Virgo supercluster of galaxies, and there's clusters of superclusters of galaxies that make up the universe.
The universe may be infinite, but Schaefer's goal was to bring our corner of it down to size.
On the first trip you went on, you probably said, "Are we there yet?" And that was a question about size. And we've been asking that eternal question ever since. How big is it?
We may have learned to grasp earthbound distances in the family car, but the distances of outer space remain vast and incomprehensible.
If you want to get to a scale where you can get the sun and the nearest star together, the Earth has to be an infinitesimal grain of sand.
Schaefer decided to come up with some simple solutions to bring the solar system down to Earth.
Hold up your thumb. All right, you see your thumbnail there? That's 1,000,000 miles across. And that's how big the scale of our solar system is going to be. And then with 1,000,000 miles being the size of one thumb, I'm going to walk to Pluto. 1, 2, 3, 38, 39, 40. Hold up your thumb, Bobby. Let's see the sun. It's so small, I can't see it. I guess if it were burning, we could see it better.
Even if it were burning, the real sun would look like an insignificant star from Pluto. Schaefer wanted to build a more ambitious model of the solar system. He started by using the planetarium dome as his sun.
So we're inside of our planetarium dome right now. It's just a little over 33 feet across, which sets the scale for our model. 42 feet's 1,000,000 miles. And on that scale, the Earth is about this big. And our star, the sun, it's 1,000,000 times bigger than the Earth is. So that means we could put 1,000,000 of these Earths inside of our planetarium dome if it were completely round.
Beginning with a 33-foot sun, the goal was to make the solar system a scale people could navigate through.
Bicycling is probably the best way because then you're using your own energy to propel your rocket.
In the real solar system, Mercury is 36 million miles from the sun. In Peoria, it is a quarter of a mile. And Venus?
Venus is here in the shopping center in the mobile telephone store.
It's about a quarter of a mile from Mercury.
So we've traveled about 93 million miles. If we had been going the speed of light, it would have taken us 8 minutes to get here. And we traveled a little bit faster on a bicycle than the speed of light, so a little bit less than 8 minutes to travel that astronomical unit, or 93 million miles. And that's all the bigger it is, 4 inches across.
Mars is about 50 million miles from Earth. On Schaefer's model, it is about 3/4 of a mile past Earth and a long walk down a hallway of the local television station.
We just spent about 3 minutes traveling to Mars by bicycle at a little faster than the speed of light. Had we been trying to get to the real Mars from the Earth, I guess it would have taken us about 450 years, and I think that's a little longer than I'd want to commit to a project.
How fast is the speed of light?
Light travels at a speed of 186,000 miles per second. That's the limiting speed in the universe according to modern physics. Now, if you want to translate that into a distance, well, it's traveling at 186,000 miles per second times the number of seconds that are in a minute, times the number of minutes that are in an hour, times the number of hours in a day, times the number of days in a year. It's a distance light travels in 1 year at that incredible speed of 186,000 miles per second, and it works out to about 6 trillion miles. Now, on the scale of our solar system, if I'm going as we are right now, about somewhere between 6 and 7 miles per hour, that's the speed of light. And this is it, Jupiter. 1,000 Earths could fit inside of it. In fact, each of those storms is as big as our planet. Everybody's astounded at the size of this planet, especially if you've been to any of the other planets. You know, when you see Earth and it's only 4 inches across, and you come to something that's 1,000 times bigger, you've traveled 500 million miles to get here in real space. And then you come to this. It's just a tremendous reward at the end of a long journey.
In fact, Jupiter is big enough to hold all the other planets and their moons. Skipping past Saturn, Uranus, and Neptune, it's a long way to Pluto.
Even at the light speed I'm traveling, it's going to take me about 4.5 hours to get there.
Pluto is 50 miles out of town. How long would it take to pedal to the real Pluto?
To really bicycle to the planet Pluto, I don't think there are enough human lifetimes to consider it.
To understand the size of our solar system, it takes the imagination of a Sheldon Schaefer traveling through Peoria and beyond.
Try this activity to complement scale. Make a scale drawing of your classroom. Measure the walls, doors, and windows. Record your information in a data table. Then select a scale to represent the classroom on paper. Using a ruler and graph paper, draw your classroom to scale.